All right, so our last section we talked about Euler circuits and Euler paths. Today we're going to talk about Hamilton circuits and algorithms. So definition first, what is a Hamilton circuit compared to an Euler circuit? Well, a Hamilton circuit is a circuit that visits each vertex exactly once, returning to the starting vertex to complete the circuit. How is that different than an Euler path? Right. Yeah, so in an Euler circuit, we can visit the vertex multiple times, but not only that, but like Sydney said, the edges have this relationship where we actually have to visit every edge. This doesn't say we have to go to every edge, does it? It doesn't. We don't have to cross over every single sidewalk on the OBU campus to do this, right? But an Euler path and an Euler circuit, that would have been the case. So with a Hamilton circuit, we're just trying to hit the locations. This is a more accurate reflection of what happens when you're trying to run errands, right? I don't care to go to every single street in between here in Walmart, right? That's not necessary. I just need to make sure I get to Walmart and get to McDonald's and get to whatever, all of my list of things that I'm supposed to get to, right? I don't need to go to all the paths along the way or all of the edges along the way. I just need to hit the locations. That's what's going on with a Hamilton circuit. So Hamilton circuit is our next example, and what we're actually going to be taking a look at is whether or not the examples given are Hamilton circuits. Check your graph. Is the graph okay? Yeah. Yes, wonderful. Okay, so we have three different circuits potentially, or paths or whatever. We have three different of these specified below, and we're trying to decide if they are in fact a Hamilton circuit, okay? So there's a couple things just in terms of the fact that it says circuit. Circuit means it does what? Starts and ends at the same place, okay? Hamilton means that I can't repeat a vertex. So that's one way that we can fail. So we can fail if we don't start and end at the same place. We can fail if we repeat a vertex. How else could we fail? We could fail if we omitted a vertex, right? That's the third way we could fail. Obviously, if we don't have, like an edge between something, that also would fail something. But those are the three things that we're typically looking for: is does it start and end at the same place? Do I repeat everything? Do I actually achieve every vertex? And then the last one would be, did I cross any edge that didn't exist, right? Did I have to walk in the grass? So we're going to take a look at our graph, and I'll use colors as well, like I did before. But we will use... we won't scribble things like I did in the last one, so we can try to use it for the same picture. The same picture for all of them. So this one tells me that I'm starting and ending in A. That's good news, right? I've already passed one of my criteria, and it has the ability potentially to be a circuit since it's starting and ending the same place. So A to E would be this one. E to C. C to D. D to E. E to B. And then B to A. Did I have any problems? Yeah. I did. What problem did I have?
You went to E twice.
Yeah. So I went to E twice. That's not okay. I mean, I'm not supposed to be able to go to E twice for it to be a Hamilton circuit. So this is not Hamilton. It is a circuit, right? Mm-hmm. But it's just not Hamilton. And the reason it's not is because I visited E twice. So we'll change colors. I'll use orange on the next one. Does it start and end at the same point? Yes? Okay, so that's one of the things. So we're going to go A to E, E to C, C to D, D to B, and B to A. I didn't visit two things. I didn't visit E twice this time, right? I didn't visit one of them twice. Did I actually go along paths or an edge every time? Mm-hmm. I did. Did I get every vertex? Did I run all my errands? Mm-hmm. I did. So this one's a Hamilton circuit. And I'm going to just jot down the things that we sort of mentally check, so when you're looking back at this later, you remember the things we looked for, right? So A to A, like it starts and ends the same place, right? Start at A, end at A eventually. There's no repeats. I went to every point, right? That's something I checked, is that I went to every vertex. And I stayed on edges. Oh, that's not going to be good. Let's do that. These are the things that I checked as I was visually going through it. Okay, there's a third one, C, right? So what do you notice about C? Yeah, it fails on that account. We'll check all the accounts, right? But it definitely fails to be a circuit at all, right? It does not start and end at the same point. So I can definitely say that it's not Hamilton. And for sure I can say because it doesn't start and end at the same point. At the same vertex. Let's see if it fails on any other accounts, just so that we're in the habit of checking multiple things. So I'll use blue this time. So I've got D to B, B to E, E to A, and A to B. Did it fail anything else? All right, it didn't visit C. And what else? It repeats B. So we didn't visit C, and we repeated, was it B? Yeah, we repeated B. This is a colossal failure. The only thing it didn't fail was I didn't have to walk in the grass, right? Like I didn't have to do that, but it failed 3 counts of things. That's pretty rough. And again, my expectation in when you're looking at multiple choice that this could show up as is something where it says something like, how does it fail? And you have to identify which of the multiple choice ones it really fails all of, right? The most complete kind of an answer that has shown up on your works before. All right. Some other pieces. Whoa. Where's my screen about Hamilton circuits? It's not there. Okay, we're missing something. I'll just write them in. No problem. We'll get it in there. Get it at the back. Okay. There's a couple of pieces of information here before we get to example 2 that seem to be missing. All right. So the first one talks about what happens when we have complete graphs. So a Hamilton circuit for complete graphs. This says the following: any complete graph with 3 or more vertices has a Hamilton circuit. Do you remember what a complete graph is? We talked about it in 14.1. A complete graph is a graph where every vertex connects to every other vertex. So it's complete in the sense that I can't add any more edges to the graph and it still be a simple graph, right? Every vertex is connected by an edge to every other vertex. So if we have a graph where every vertex is connected to every other vertex, we will be able to find a Hamilton circuit, okay? That's not the only thing, though. So there's one more here that says when we want to talk about when Hamilton circuits are the same or considered the same. By the way, let me mention before I keep writing, this does not say it has to be complete to have one. Did you notice that? That's not what it said. It doesn't have to be complete to have one. In fact, I don't think that the graph we did over here was complete. Go back to the first one we just did. One more back. This is not a complete graph. There is no edge from A to D on this graph, for example, right? But it had a Hamilton circuit. We found one. So we don't have to have a complete graph for it to happen. But what it says is if we do have a complete graph, we know it will have a Hamilton circuit. Okay? So be careful in the structure of that logic. So when Hamilton circuits are considered the same. Hamilton circuits that differ only by their starting point will be considered the same. Circuit. So I want to go back to the example that we did before and just show you an equivalent, right, an equal or the same circuit to the one we already had. But I also want to give you a real life example of where this is used. So we're going to take a look over here. The one we had. Part B was the one where we had a Hamilton circuit. We started at A, we ended at A. But we could pick up and start somewhere else. So let's say, for instance, instead we started at C. Well, we could start at C. And if we went from C to D, D to B, B to A, and then A to E and E to C, so we're going in the same order, we're just doing like a cycle, right? That would be considered the same circuit. So this would be something like, and I'll write it in yellow here. So if I went C to D to B to A, and then from A to E, and then back to the C where I started, that's the same Hamilton circuit. You're doing everything in the exact same order, you're just starting at a different place. I have a couple of examples in real life that are not near as common in my life now as they have been in the past, but my husband used to play golf, and he would do things called scrambles every now and then in a golf. And a golf scramble, what happens in order to make sure that you don't all arrive at the same hole at the same time is that you have up to, if it's an 18-hole course, you're going to have 18 groups of people going out to play golf, and they all start at a different place. So you may start on hole 1, somebody else starts on hole 5. But you all progress through the holes in the same fashion. That way you don't all end up at hole 4 and have to end up waiting on each other. That's an example of the Hamilton circuit. Another thing that used to happen back in the day, and this is ages ago, at least in my world, like when I was a child, is that we used to do, at least my parents' Sunday school class used to do, they were traveling dinners. I don't know if that's what they were called, but what you did is, again, there was a progressive dinner. That's what they called them. They called them progressive dinners. And so there would be different homes in the circuit, if you will, of your Sunday school class or your church or whatever. And you would go to this particular person's house and you would eat this course of the meal. And then you go to the next person's house and you would eat this course of the meal. And everybody would go in a different order. So some people started with dessert, right? And they ended with the appetizer or something like that. So you wouldn't necessarily all get the same food in the same order, but you'd go to the houses in the same order, but you'd start at a different place. So those would be considered Hamilton circuits. All right, so let's take a look. Yeah?
I don't know if you know about this, but in music, there are things called church modes. And basically all it is you stay in the same key, but you start the scale in a different place.
Okay,
So
same
if you know
idea.
music, that's all.
Yeah. There are other examples, I'm sure, as well. In fact, the progressive dinner just occurred to me like 10 seconds ago when I was thinking about my golf scramble example, and remembering from when I was a child. So we're going to take a look at another graph. Does it look right on your paper?
Yep.
Yeah? Lovely. Okay. So we're going to determine whether the graph has a Hamilton circuit. If so, we're going to find one. And if we find one, there's often, in any case, many different answers that are correct. So for starters, if the graph is complete, we know it's going to have one. So that's a good place to start and to decide, is the graph complete? No. It's not a complete graph. What's missing? I know I don't have a lot of details written here, but can you give me an example of one?
A connection from U to V.
Yeah, U to V is not written in, correct? So it's not a complete graph. That doesn't mean it doesn't have a Hamilton circuit, but it means that we aren't guaranteed one. Make sense? So it's not complete. It's a good thing for us to sort of at least note. Too thick. It's not complete, so there's no guarantees. So what we do is we simply attempt to try to find one. Okay, so we need to attempt to try and find one. We get to pick kind of where we start as well. I'm going to choose to start at point X so that we're all starting at the same place. So from X, we'll see if we can get this to work for us. And if we start at X, where would you like to go from X? Our goal is to visit all the vertices, remember? But we don't care if we pass through all the edges. So where would you like to go? W. Okay, U to W. Then where? V. Sydney, you want to keep going for us?
Yeah.
Okay, what's next?
T.
Okay, so V to T.
Oh,
It'll work. You can keep going.
U and then back to X.
And then U and then back to X. This is not the only one. In fact, it's probably not the one that I have written down. It's not. Okay, so there's lots of options of things that will work. As long as we find one of them, we're good to go. Okay. And again, my expectation when you look in my math lab is this is probably a multiple choice question where you're verifying which one of the 4 choices or something that they give you actually would work. You're not actually starting from scratch to find one because there's not a real good way to enter that into their system. Good? All right. Take a look at this. We're going to try and decide whether the description that we're given is describing an Euler circuit, a Hamilton circuit, or neither. So it has to tell us what the vertices are and what the edges represent. The vertices are going to represent places in a botanical garden where the paths cross. Okay, so the paths themselves are going to be the edges. The places are going to represent the vertices where they cross. And a visitor wants to walk along each path exactly once, returning to his starting point. What is it describing? It's describing an Euler circuit. What is the clue to knowing that this is an Euler circuit? Exactly. It's about describing the paths, not the overlapping pieces, right? Not the places where they cross. And saying that they're exactly once tells us it's Euler, as opposed to just any old path or any old circuit or something, right? So yeah, I want to cross each path, each sidewalk, if you can imagine. Now, if you changed this and tweaked it just slightly, and instead you said they wanted to visit each location, right? Think about like going to the zoo. You might not care that you pass every point at the zoo once, right? But you might want to make sure you visit every animal's display once. That would be an example that would be Hamilton, right? Don't really want to see the giraffes twice, right? So if I'm not wanting to visit something twice, that would be a Hamilton circuit instead. And I got to start in the same place, otherwise I can't get back to my car. Agreed? Yeah. All right, so let's take a look then at how many of these exist. Because I mentioned on the one that we did, number 2, lots of them are going to exist. Yours might not look like mine. Mine did not look like Sydney's for my paper, all of that kind of. How many of them are there? Well, if you have a complete graph, we didn't on number 2, but if you did have a complete graph with n vertices, we would have n minus 1 factorial Hamilton circuits. And we've seen factorials before, right? We're revisiting them. We saw them in chapter 10, the one we just did, right? Chapter 10. What does 4 factorial mean? Yeah, 4 times 3 times 2 times 1, which would give me 24. We're going to come back to that 24 in a moment with an example. That's a lot. So there's not quite 24 of you in this class, I think, which means every single one of you could pick a different path. And it would be a booger to grade. It'd be awful, right? It really would. If I were to write out all the options, right? That would be terrible. Every one of you could have a different circuit and it would work. Could work. All right, so this example, the ones on the screen right here, is asking us to find how many Hamilton circuits there would be in a complete graph with 10 vertices. But it says we get to leave it in factorial notation, so that's nice. We don't even have to finish it out. So if there's 10 vertices, how many Hamilton circuits do I have? 9 factorial. It's just one less. All right, you ready to look at another type of graph? It's not exactly another type, but it's got additional information that we haven't seen before. A weighted graph. A weighted graph is a graph with numerical values associated with each edge. And weighted graphs, though you've never thought about them that way, is actually what your Google Maps and things like that are using. So typically speaking, when you're looking at like a map in your phone and it's telling you how to get somewhere, the weights it's using is the time it takes to get between certain pieces of your path along the way, right? You're not interested always in conserving like the shortest distance. We're not talking about as the crow flies, like I've talked to you about before. You're usually interested in time. At least that's what your phone is typically trying to do for you, is minimize the time it takes. Now, that's not the only way it could do it, right? It could be minimizing the distances. That might be more beneficial in terms of your gas that you're expending, correct? But typically, it's looking at time. So a minimum Hamilton circuit is the circuit that has the least possible weight. So in our description, it would be the least possible time that your algorithm in your phone is trying to create for you in some sort of a GPS situation. And we're going to look at what's called a brute force algorithm. It means it's forcing it to happen. So the brute force algorithm says to choose a starting point and list all Hamilton circuits with that starting point. Then you find the total weight of each circuit, and then whichever one's the least value is the one you use. And in some fashion, your phone is doing this, but it doesn't really do this completely. So we'll get to what your computer or your calculator or your phone or your GPS, whatever's really doing in a little bit. But this would be finding the absolute minimum because it's finding every single possible combination and comparing them.
I didn't get to finish writing what the minimum was.
Oh, whoa, 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 whoa.
Sorry.
Just pushed the wrong button.
Okay.
Got it? Sorry.
You're good. That's good.
Are you good, Nathan?
Yeah.
Almost? Okay. Did everybody get this one written down? Almost? Okay. Fair warning, you're not going to like the next problem. Okay? But it should be the worst one we see today. How's that, too? We're going to get it out of the way. All right, so what we're going to use is we're going to use the brute force algorithm. And we're going to do exactly what it says, and we're going to list all Hamilton circuits with a starting point. We're not going to find the total weight of every single circuit because that's going to be super time consuming and not worth our time to continue. But we'll do a few of them so you can see how the process works. All right, so check and make sure my picture matches your picture. I think that it will. Okay, so I tried to put them in yellow on my screen so they'd stand out a little bit more than writing the white on top of the white edges and so forth. So we need to pick a starting point. It's sort of arbitrary. I'm going to pick G just because it's at the top, and then we're going to do this together. We're going to do kind of like what we saw happen back in chapter 10, the very first section where we listed all the ways of making a committee that had certain criterion. Do you remember doing that? It was kind of annoying, right? Okay, so tell me first, looking at this, is the graph complete? It is. How many vertices are there? 5. So how many Hamilton circuits will there be? 4 factorial, which was 24. We're going to write down 24 different ways that we can go from G all the way around this sucker. All right, you ready?
No.
That's what we're going to do. Okay, we're going to be ready anyway. Okay, so we're going to make sure we try and list all of them by carefully listing all the pieces. So G could go to what? Pick me one point.
C.
What? What?
C.
C. G to C. Okay, so if I do GC, I can do GC several times before I run out of options. So let's do GC. GC what?
D.
D. I can actually do GCD a couple of ways before I actually run out of options too. GCD, then what? E. F. And then back to G, right? Or I could do F, E, and back to G. Agreed? G, C, D, E, F, or F, E, back to G. Are you good with that? Okay. That's the only ways I can do GCD and then finish it out. So what I need to do now is to go back to the GC, not on campus, but the GC, and not go to D next. So pick me something else besides D. E. So there's going to be a couple of options of ways I can go to E. E what? Well, I could do EF. And if I do EF, what's next? D, and then back to G. Or I could do DF, and then back to G. So I've done GCD, GCE. What's my next option? GCF. And there's going to be a couple of those, GCFs. Well, GCF, what could I do next? D or E. If I do D, then I do EG. If I do E, then I do DG. So we're trying to keep things stationary as much as we can to make sure we don't miss writing one down. Do you get that feeling? I hope so. At this point, I have explored all there is to explore from going to G to C. And I need to pick something else as my second point. I don't need to change G. Remember, Hamilton circuits don't have anything different if I start at a different point. So everything I start with is going to start with G, because starting at a different point just creates another circuit that's the same, like our golf scramble. Okay? So I will still stick with G. How many did I get? 6. How many more do I have? 18. All right, so let's go to G next with something else besides C. G what? D. So I'm going to have 6 of them that are going to start GD. Okay? GD what? E. So I have 2 that'll be E's, I have 2 that'll be C's, and I have 2 that'll be F's. Right? They're occurring like that in pairs all the way along, so I might as well write them that way. Just like over here, right? GCDs, GCEs, GCFs. Okay, after I do GDE, pick something. F, which means then I would have to do C and then back to G. But I could have done CF and back to G. All right, GDC, E, E, F, G, LMNOP, F, E, G. Okay, G, D, F, E, C, G, or C, E, G. Those are all the ones that start out with the letters G and then D. We're halfway there, right? Yeah, I can tell you some of you're already done. Okay, that's all right. You're doing great. Let's put the next one just beside these. I'll draw a line here so that I don't get them confused. I don't want to do GC and I don't want to do GD, so what could I do next? GE, and there's going to be 6 of them. Okay, GE, what could I do next? F, so I'll have 2 Fs, F on 2 of them, and then D on 2 of them. GED, like your high school equivalency. What else?
C.
C on both of them. All right, once I get those options in place and stuck, GEF means I have C and D, or D and C, always returning back to, D and C, always returning back to G. How about GED? CF or FC and back to G. How about GEC? DF or FD and back to C. I'm sorry, back to G. And then my other 6. What am I left with?
GF.
GFs. So 6 GFs. GF, GF. Okay, after the G and the F, what could I do? D or C or E. So if I do G, F, D, now what? C, E, oh my goodness, I can't write. C, E or EC and back to G. How about GFC? DE or ED and back to G. And how about GFE? CD or DC, like the comics, back to G. Okay. All right. Do I have 24 of them? Oh my goodness, yes. Okay, but pause for a moment and take a look back at what it says we would actually really do if we were doing the brute force algorithm all the way out. We've accomplished 1, and we've accomplished 2, and what we would have to do for 3 if we were really doing this whole thing out. All of their total weights and add them together. It's 24 different summations. Who's signing up? Do you want to do it? That sounds terrible, doesn't it? It really does. I mean, like, it was bad enough that we had to write out 24 of them, right? I don't want to calculate all of these for 24 of them. We'll do just a few of them so you can get a sense of how we would find an individual one of them to do this, because we haven't done one of these weighted graphs before. But we're not going to do all 24 of them. So let's just do maybe the first one from each of our lists. Let's do that, because they're actually written in such a way I have some space above them. All right, so I'm just going to write the value of the weight of each of them. So what is above, what is, if I'm going to do the G and the C, what is the weight between G and C? 10. How about between C and D? 12. How about between D and E? I'm just taking your word for it so I don't keep zooming out. What about between E and F? 17. F and G? 15. And somebody's going to grab a calculator and add that together for us. 54? Do I have a second on the 54? We're not really voting, but do we have somebody who says I agree? Oh, I've got 44, 54 to 64. Is it 64? Oh dear. Okay, 64 is what we're going to go with. That one's 64. All right, let's just do the next one that's next to it. G, F, D, C, E, G. So how about GF?
15.
FD.
21.
DC.
12.
CE.
13.
And EG, excuse me.
13.
Okay, and if we add them together, how much do you have?
I got 76.
76. Oh, I got 2 people on 76. We're going to call it good. Okay, 76. All right, let's do 2 more of them, the ones that are at the top of the next list, actually. I need to shift them down or I'm not going to have any space. Okay, GD. Did I get them shifted okay? Oh, my G just hanging out there in the middle of the air. Oh, my goodness.
And there's one that
There's another one too. Did it run into something?
Yeah.
Oh, it did. Oh my goodness. Wow. What did I do? There's a G. Is that an F?
Yeah.
We're going to go. Oh, that's the wrong color. Whew. Okay, there we go. You look okay?
So we don't count them all out.
All right. We're not going to count them all out. That's right. Okay, let's take a look. G to D. 15. D. E.
10.
10. E. F.
17.
F. C.
15.
C. G.
10.
10.
Actually, I think DG is 13.
D. G is 13 at the beginning.
Yeah.
Okay. 13, 10, 17, 15, and 10. What's my total? 65? Okay, so considering the 3 I have so far, the one that's the smallest is the first one I did, right? They're not going to always be the same weight. In fact, they typically aren't. And then the last one that we're going to do together, not because it's the last one we could do, but because we're going to cut it short. How about GE?
13.
EF.
17.
FC.
15.
CD. Oh, which one is it?
12.
12? Okay, and then DG.
13.
Okay, adding those up, what do we have? 70? Okay, so we did 1/6 of the summations right there. We did 4 out of the 24. Brute force algorithm, we would actually do all 24 of them if we were finishing it out completely and finding the minimum one of them. And we would be spitting back that back out and saying, this is the path you should take to do this, right? To minimize gas or to minimize distance or to minimize time. Those are some things that we would be minimizing from a maps standpoint. This is not very practical. Agreed? And this is a small graph, to be perfectly honest. It had 5 vertices. That's very small, right? Think about what your actual phone or your GPS does when you're trying to go from one city to another city. How many different ways could you really go between those places? More than that, right? There's far more options of things you can do. So that's really not practical. We would rather have an efficient algorithm. An efficient algorithm is an algorithm that doesn't take much time to compute, specifically for a computer. But even for you, it would be more efficient if it were faster. That's what efficient means. So we tend to go back to saying, well, let's find an approximate algorithm. So approximate algorithms are algorithms that are efficient. They don't take the computer much time to do them. And they give reasonably good solutions most of the time. It's so touchy-feely sounding. Reasonably good most of the time. This is what your phone does. It uses approximate algorithms. And that's why every now and then you're like, I don't really think that's going to be my best bet. I think if I do this other way, and you're like, oh, look, I actually found a way to do it faster than my phone originally said. Why did it do that? Well, because it wasn't finding brute force all the ways of doing it. It was doing something that was sort of efficient and approximate along the way. So we're going to do one. It's going to be a smaller graph, but you're going to see how we go about finding an approximate one instead. And the way that that's done is with what's called the nearest neighbor algorithm. So for the nearest neighbor algorithm, we choose a starting point, unless we're given a starting point, of course. Call it A or whatever. And you choose the edge that's the least weight connected to that vertex that you start with. So of all the different paths, you have the option of all the different edges, you have the option of you pick the one that's the smallest number. Okay? And then once you get to that vertex, you do the same thing again. You pick the one that's the smallest number. The only thing you have to do to be careful is that you need to make sure that as you're making those choices that you don't actually complete a circuit or something that keeps you from finishing, going around all of the points. So at each vertex, you repeat this step 2 as it applies to the vertices not yet visited. So you only visit the vertices you haven't yet visited. And you do this until you have visited all the vertices and returned to the starting one. It's not perfect. It's approximately a good solution most of the time. Okay? So as you're doing that, you might find yourself thinking, I'm not really sure that gave me the least weight, and it might not have. But it's going to be close. And most of the time, it's going to be close enough. And in some sense, this is what happens in your phone. It's looking for minimizing, usually time, close enough, and giving you an approximate solution that's a good one. Okay, so we have a simpler graph. Let's make sure that it looks right on your paper compared to my screen. Does it look okay? Yeah? Lovely. Okay, it says to use the nearest neighbor algorithm to determine an appropriate solution to the problem of finding minimum Hamilton circuit for the graph. In each case, find the total weight of the circuit. So we're not finding, in this case, it's only got 4 points, so we're not finding all of the Hamilton circuits. We're just doing it with this nearest neighbor algorithm. So the first one, part A, tells us to start at F. So we start at F, and we're just going to write down, like we did before, the locations. This is F. Where will F go if it's going for the least weight edge? To H. Okay, so after I go from F to H down here, H has 2 options. I can go up to I or I can go over to G. Which one will I choose? I will choose to go to I because it's the smallest. Now, while I to F is not the smallest, even if it were, I couldn't do that. I have not yet visited point G. So at this point, I am stuck with whatever is on this diagonal G to G. I have to do that next. Otherwise, it won't be a circuit that's a Hamilton circuit that visits everything. And then I go back to the starting point F. So this is the order of my values if I start out with this idea of choosing the minimum weight. And then we want to do the same thing we did on the last screens where we actually find those values. F to H is 2. H to I, 4. I to G, 3. And G to F?
6.
6. And what is my total weight?
15.
15.
Sorry.
We're going to do the same thing for part B, but now we're actually starting at G. Notice there's no other options with this algorithm. I'm not finding every possible scenario. I'm following a very strict guideline of how I make my choices. How about starting at G? Where would I go first? I would go to I. So I would actually go across my diagonal first, G to I. Where would I go after I?
H.
I to H. Now, again, at this point, I have no choice, no matter what happens next, because I've missed a vertice. I have not gone to F yet, right? So I must go to F, and then F will take me back to G. What is the weight for G to I? I to H. H to F.
2.
And F to G. Ooh, so we had to pass through the 6, which is not preferable, but we're stuck at this point, right? It's a pretty big weight one, but we're stuck. So we did, at least we've avoided GH along the way, right? How about if I add all these together?
15.
15, and I end up with the same 15 I had before. That's coincidental. We do not always end up with the same one as we saw on the previous example.